This is section 3.8, implicit differentiation. So the idea is, if you have an implicit function of y, what does that mean? It means y hasn't been solved for directly. So at the top here, I have an explicit function where if you wanted y prime, you could just say, oh, y prime is 2, take the derivative. This is an implicit function. It's not solved for y. It implicitly defines y as a function of x. Sometimes it's not possible to solve for y, and sometimes it's hard to solve for y. So the question is, can you find y prime without solving for y? And the answer is, of course, yes. That's what implicit differentiation is. And so before I can show you how to do that, I need to show you how to do just the basic implicit differentiation. If you're taking the derivative with respect to x of any function of x, that would be the left-hand column. It's going to be a normal derivative. In this case, here we're going to take the derivative of x, which is 1. Here, derivative of x, use the power rule, 2x. Sorry about that. This one, the derivative of sine x, is cos x. However, if we take the derivative with respect to x of y, that's the second column, we have to use the chain rule and think of y as a function of x. So this is actually going to be y prime. Or you can use, if you want, the notation dy dx. They're the same. Students have indicated to me when they're doing implicit differentiation, they prefer the y prime because it occurs so often in their equations that it's kind of messy and hard to keep writing dy dx. Okay, this guy, before it was 2x. d by dx of x squared is 2x. But d by dx of y squared, we use the chain rule. 2y, leave the inside alone, the new exponent is 1, then multiply by the derivative of the inside, which is y prime. So 2y, y prime. Again, chain rule on sine y, we take the derivative of the outside, which is cos, leave the y alone, and then multiply by the derivative of the inside, which is y prime. And I'll put that out front. Okay, and I'll just do one more column. If you had been doing d by dy of y, that would have been the same as the first column. You've just changed x's to y's. That's 1. d by dy of y squared is 2y, which is normal derivative. So what I want you to see there is what's different about the second column is that you're taking d by dx of y. The variables are different. Okay, a common calculation is d by dx of xy. And so just remember when you do that to use the product rule because x is a function of x, but so is y. So d by dx of xy is the derivative of the first, which is 1, times the second, plus the first function, which is x, and the derivative of y is y prime. So y plus xy prime. Why are we bothering to do this? This is an example here where I'm just showing you it's not always easy to solve for y, so you can take the derivative directly. If you use a computer to solve this function here for y, you get 3 really long answers. 2 are complex, and this one is just one of the answers. This is the real solution. And who would want to take the derivative of that? Nobody. That's a nightmare. Okay, so here's how to use implicit differentiation. You're going to take d by dx of both sides of the equation you're given. Then you're going to solve for y prime. Now that's all algebra, but that's usually the part that students have trouble with. Okay, so I spelled it out for you. Take all the y prime terms, move them to the left-hand side, take everything else, move it to the right, factor the y prime out of the left-hand side, that's LHS, and then isolate y prime. I'll show you that with an example. Okay, so find y prime for this equation, then find the slope of the tangent at 2, 1. The slope of the tangent at 2, 1 will be y prime evaluated at 2, 1. Straight bar means evaluated. Okay, step 1, d by dx of both sides. Now, I know this first step is just notational, where you're actually not doing anything, but it's important to do this step. It's like using your blinker when you're driving. It's indicating to people what you're about to do. So if someone's reading your work, they could say, oh, I understand the second line. It came because this person took d by dx of both sides of the first line. All right, so now let's take the derivative. The derivative of x squared is 2x. The derivative of y cubed, we have to use the chain rule, 3y squared y prime. And then that equals the derivative of 5, which is 0. Now we solve for y prime. So move the 2x to the other side, and we get 3y squared y prime equals negative 2x. Divide by 3y squared. Y prime is negative 2x over 3y squared. And there's our derivative. Notice that the derivative will usually involve x and y. If we knew what y was in terms of x, we wouldn't be doing this to begin with. So that's the first part, find y prime. The second part is to find the slope of the tangent at 2, 1. So for that, we want y prime at 2, 1. So I put 2 in for x and 1 in for y in this formula here, and I get negative 4/3. So that's the slope of the tangent line at 2, 1. And I did that without ever solving for y, which is pretty amazing. Okay, let's do a slightly harder one. So I'm going to make them progressively more difficult as we go. Step 1, d by dx of both sides. That's d by dx of y squared. Now we take derivative. 8x minus 5 plus product rule. The derivative of x is 1. So 1 times y plus x times the derivative of y, which is y prime. So we did that on the first page. And that's equal to, chain rule, 2y, y prime. So now let's move our y prime terms to the left and our non-y prime terms to the right. So this has a y prime in it, so I'm going to leave it on the left. This has a y prime in it, so I'm going to move it to the left. Everything else I move to the right. So 5 has no y prime, so I'm going to add 5 to both sides, and I'm going to subtract 8x from both sides. Oh, and y, missed one term here. Y has no y prime in it, so I'm going to move that over also. Okay, so now y primes are on the left, non-y primes are on the right. Factor the y prime out of the left, so there's only a single y prime, x minus 2y. The right just stays the same, 5 minus 8x minus y. And then finally, to isolate y prime, I divide both sides by anything that's being multiplied by y prime, in this case, x minus 2y. So I'm going to move up here and write my final answer. Y prime is 5 minus 8x minus y divided by x minus 2y. So you can see that this step, taking the derivative, was actually pretty quick, but it's the algebra that takes the longest time, solving for y prime. Okay, let's do another one. You might want to pause it and see how you do on your own. Okay, hopefully you did that. So let's take d by dx of both sides. D by dx of tangent y. Okay, for the first expression, I need the product rule. Y plus xy prime. All of that is the derivative of xy. Then I want d by dx of cos x, which is just normal derivative. Since cosine starts with a c, its derivative is negative sine x. Okay, and then that equals the derivative of tangent y. Chain rule. The derivative of tangent, leave a space in front, is secant squared. Leave the argument alone, the baby, and then multiply by the derivative of the inside. The inside is y, so its derivative is y prime. Okay, so now we take our y prime terms, move them to the left. So xy prime just stays over here, xy prime, and I'm going to subtract y prime secant squared y. And then on the right, I'm going to move the sine x over, it becomes positive, subtract y from both sides, so I get minus y. All right, then factor the y prime out. X minus secant squared y equals sine x minus y. And finally, divide both sides by x minus secant squared y to get y prime equals sine x minus y divided by x minus secant squared y. And there's your answer. Next page, let's do an application problem. The volume of a cone of radius x is 1/3 pi x squared y, where y is the height. If the volume is 132, find dy dx when x is 6 and y is 1. All right, so we're told that the volume is fixed, 132. So let's rewrite that equation. 132 equals 1/3 pi x squared y. We want dy dx, so what we're going to do is take d by dx of both sides and use implicit differentiation. And we'll be using this a lot when we talk about related rates. So this isn't going to go away. 1/3 pi x squared y. Okay, d by dx of 132 is 0 because 132 is a constant. Now, for the next term, pi over 3 is a constant. So you can actually write this as pi over 3 times d by dx of x squared y. So I'm going to put a pi over 3 here, and then take the derivative of x squared y. We need to use the product rule. So the derivative of x squared is 2x, and then I multiply by y, that's my f prime g, and then I add on x squared, that's my f, and my g prime is y prime. So I want to solve for y prime. Now, since I've got 0 on the left, I'm just going to multiply both sides by 3 over pi and get rid of it. So 0 times 3 over pi is still 0, and that just gives me 2xy plus x squared y prime, which is a lot easier. All right, so now I'm running out of space, so I'm going to move up here. I'm going to write x squared y prime equals negative 2xy, and then divide both sides by x squared to get y prime alone. Negative 2xy over x squared, which is negative 2y over x. All right, there's my derivative, y prime. So I'm almost done. I want y prime at x is 6, y is 1. So y prime evaluated at, I'm going to use a different notation instead of straight bar. I'm going to just say when x is 6 and y is 1 is put 1 in for y and 6 in for x. So that's negative 1/3. Okay, so that's it. And that's the end.